Hello everyone. In the previous lecture, we had a look into the different methods of carrying out the survey in the field, that is electrical resistivity survey in the field. There are three principal methods of carrying out the survey in the field, which are: number one is profiling, number two is sounding, number three is 3D tomograph. So, first one is profiling, second is sounding. So, we had a look into electrical profiling, how electrical profiling is carried out in the previous lecture. How electrical profiling is carried out, we progressively move the electrodes along a profile. So, our center point keep changing, right? These are our station 1, 2, 3, 4 like that. We plot distance versus apparent resistivity. We are, after having seen that, we are looking into some of its applications. Right. Here is a study carried out by the United States Geological Survey. Right. What they have done is they carried out electrical profiling along this area to bring out the subsurface geological configuration. So, the survey has been carried out with two different electrode spacing. Right. Hope you can remember, electrical profiling can be carried out in different electrode configurations. Right. That means you conduct the profile initially with, for example, here the distance between A is 1 meter. You can do one more survey with 2 meter distance. Right. This is station 1, maybe 2, 3. So, here it was A is equal to 1, here A is equal to 2. Similarly, here these researchers have carried out investigation for different depths to bring out the subsurface geology. Right. From the way in which the profile was changing, what is evident here is whether A is 30 or 60, at this location the resistivity values were higher. Why the resistivity values are higher? Correspondingly, if you look at the geology beneath the surface, we have sand and gravel. Right. Above sand and gravel, we have clay. Here too we have clay. Compared to clay, we had seen previously, sand and gravel will have higher resistivity because clay is having highest porosity. So, clay will have large amount of moisture. Sand and gravel also will have moisture, but porosity of sand and gravel is much lesser than clay. For clay, if you clay porosity can be maybe about 50%, certainly 40 to 50%. For sand and gravel, porosity will be only about 15 to 20%, almost half, less than half, due to which compared to clay, sand is having higher resistivity. That is what has been picked up by the electrical resistivity profiling. So, this is how we are able to understand about the subsurface. So, precise configuration cannot be understood, however, we need to do couple of drillings, right, to bring out the proper geological section. But what is evident is profiling is able to bring out, possibly in this case they have identified a buried channel, right. This was the previous channel, right, along which a river would have flown. Subsequently, the river has migrated, the entire channel got buried beneath the surface. That was brought out by the electrical profiling method. Then the next is the electrical sounding. So, first is profiling, then sounding, third is 3D sounding. So, we had seen with some more in a detailed way what is electrical profiling. Toward the end, I showed you couple of case studies. Next is sounding. In sounding, our interest is to know vertical variation in the lithological formation. Our interest is to know the vertical variation in the lithological formation. Right? What was our interest in profiling? In profiling, our interest is to know lateral variation. That is what we have done. So, from along this section, we did the survey in a profile. We kept the electrodes at same distance, all the 4 electrodes. You can see my fingers, all these 4 electrodes were progressively moved along a profile to understand the subsurface variation in a lateral direction. Whereas here, our interest is to know how vertically below the surface the lithology changes. How can we achieve this? We have already seen depth is related to the distance between the electrodes, isn't it? So, what we are going to do is we are going to progressively increase the spacing between the electrodes, but we will keep the center point as the same. That means our station location will remain the same. So, for example, this is our station location. So, in station location is remaining the same, but what we are doing? We are progressively moving the distances between the electrodes, right? Initially, we keep them at this distance, then at the same station, we increase this is our station. Imagine we are doing by Venner method. So, this is the first arrangement. A is 1 meter. We completed. Now, I am just erasing that. Now, we are increasing the electrode spacing like this. Next measurement. So, this is how the center point remained the same, but we progressively shift the electrode symmetrically on either side. Okay. So, we try to understand what is the lithological variation in the vertical direction below the surface. So, that is what I have written here. Electrodes are expanded about the center point. Usually, what is the distance we should start with? That is what has been stated here, right? Usually, in a multi-layer case, the distance A, if you are using Venner method, or AB by 2 has to be lesser than the thickness of the expected thickness of the first topmost layer, right? So, this is the ground surface, right? We expect presence of soil, maybe then weathered rock, fractured rock. Okay. In such a situation, imagine the thickness of the soil is expected to be, let us say, 2 meters. If it is 2 meters, we should commence our sounding, right, with a value less than 2 for A, or with a value less than 2 for AB by 2, depending upon whether we are going to choose Venner or Schlumberger. Okay. So, here let us discuss about which method of electrode arrangement will be better to carry out vertical electrical sounding. What do you think? Hope you can recollect Venner method and Schlumberger method. For conducting profiling, which method is preferable? We had a discussion in the previous lecture. Which method is preferable to conduct profiling? It is preferable to use Venner. Why? Because at the field there is no confusion. We can instruct our people to always arrange the electrode at same distance, right? We can progressively move, shift it here. Then after completing this, shift it to this place, shift it here, carry out one investigation, that is for this station. After completing this will be our investigation location, shift this electrode to this place. So, this is how you can shift and carry out the survey. Venner method is easy. Whereas, to carry out a depth sounding, it is preferable to use Schlumberger method. Why? In Schlumberger method, there won't be any need to change the potential electrodes, because as per this, it is preferable to, as per Schlumberger, it is sufficient enough to keep the distance between A and B at a distance greater than 3 times of Mn. This is the condition. So, it is not necessary to change the distances between the inner electrodes often. So, which is of greater advantage to us, isn't it? So, it is better we conduct vertical electrical sounding by Schlumberger method. This is my view, right? But we can do by any method as shown in this diagram. You can do by Venner or Schlumberger or dipole. In any way we can do, but during the investigation in the field, I find it easier to go with Schlumberger method. Why? Because there is no need to frequently move the potential electrode. Suppose if you are using Venner method, always we need to shift the 4 electrodes. If you are using Schlumberger method for sounding, it is preferable to just shift the current electrode on either side. Potential electrode need not be disturbed often. Okay. So, this is how vertical electrical sounding is carried out in the field. What is the aim here? Aim is to increase the depth of penetration of current to understand greater depths, right? So, when you conduct vertical electrical sounding, let us imagine by Venner method, what is the data we are going to get? We are going to increase the value of A gradually, right? How are we going to do? This is the area we need to investigate. This is our station. If you are using Venner method, first I would have arranged the electrodes like this. What is the A value for this? A value for this may be 2 meters, right? When I arranged it at 2 meters, I note down the V value and I value. But I had told you already, today's modern resistivity meters directly give the value of rho A. To give the value of rho A, we have to feed in A. Otherwise, it gives the value of R, let us say 0.23 ohms, right? Then we determine the apparent resistivity. How? Apparent resistivity by Venner method is equivalent to this, right? We have completed one measurement. Now, I decided to do for 3 meters, which means I am going to increase the electrode spacing. I am removing this as well as this. I am going to keep it at this distance. This is my new location. They are now at 3 meter. Every electrode is at 3 meter distance. I note down the next value. This is how I prepare my data. I get the values of apparent resistivity. So, this is how we obtain data in vertical electrical sounding by Venner method. Next, let us see how the data table will look like when you use Schlumberger method, right? So, in Schlumberger method, there is no need to frequently move the potential electrodes. Only the current electrodes are symmetrically moved on either side. That means I will draw a diagram again. So, this is the ground surface. This is our station. We want to know how the subsurface is beneath this location. That is our aim of this work. I arrange the potential electrode like this. This is M and N. These are the current electrodes. Okay. A and B. What is the distance between A and B? A and B, let us say, is at 4 meters. distance between A and B is 4 meters. So, the distance between M and N has to be, let us say, we have kept it at 0.75 meters. Okay. I have taken one measurement. I enter the values. AB is 4. Here for convenience we are writing AB by 2. AB by 2 is 2 meters, and here also we can have Mn by 2 or Mn by 2. Mn by 2 is 0.75 divided by 2. So, 0.75 divided by 75 divided by 2. Okay. Then for this configuration, what is the value of R? What is the value of rho A? So, rho A can be calculated using this formula, whereas here constant K depends on the distances between Mn and AB. Okay. After taking one reading, then we are going to move only the A and B electrodes. This will be my new location. A new location. So, now let me say AB by 2 now may be at 3 meters. I am getting a new value of rho A. Then changing AB by 2 to 4 meters. But Mn by 2 is at the same distance. What distance? 0.75 by 2. But what may happen during the survey is, after you increase the distance between A, B to some greater distance, the equipment won't be able to pick the potential. Why? Because current electrodes are very far. Okay, current electrodes are very far, but potential electrodes are very close to each other at the center. So, the equipment may not be able to pick the potential. So, what we need to do is, after carrying out the survey for 4 or 5 AB by 2 values, we will also increase the distance between Mn. We may increase it to, now let us say, we will shift the Mn also to some greater distance. This is my new Mn. Mn is, let us say, at 2 meters. So, Mn by 2 value will be 1 meter. Then we again increase the distance between AB, carry out survey for 4 or 5 locations. Again we will increase the distance between Mn. Is it clear? I will repeat again, right? That means when you do the survey, M and N is very close to each other. This is the location of A and B. Now, after making one measurement, you are shifting the electrode symmetrically on either side. This is the station number. This is the location number of current electrode. Initially, I am using this letter. This is the new location. This is the third new location. After that, I also move the potential electrode to greater distance, then continue. So, this is what is known as depth sounding. That means what we are doing here indirectly, we are increasing the depth of penetration to each electrode configuration. That is our aim, isn't it? Our aim in this is to understand the vertical variation beneath our station. Beneath our station, I want to know vertically how the subsurface changed. So, we have seen both the cases, right? In the previous slide, we had seen how we will obtain the data by Venner method. Here, we have seen how do we obtain data by Schlumberger method. Whatever method you use, the center point remains the same, right? Now, what is the purpose of doing the sounding? So, we can prepare a plot of, right, what is known as apparent resistivity or resistivity curve. Resistivity curve is prepared as a function of log of electrode spacing. versus apparent resistivity, right. So, we prepare a plot of electrode spacing and apparent resistivity. That is what we have obtained. We have seen on in the previous slide. For example, this is for Schlumberger method, this is for Wenner method. So, we end up in having a data of, in Wenner method, what data we get? A versus apparent resistivity. What is A? Which is electrode spacing. Apparent resistivity is designated by rho A. Whereas in this method, what is the data we get? AB by 2 versus rho A. What is AB by 2? Half of the distance between A and B. What is rho A? Rho A is apparent resistivity. What is the depth of penetration here? Depth of penetration is AB by 2. In previous slide, depth of penetration is A. So, indirectly now we have an information on depth versus apparent resistivity. Okay. So, this plot is, though we write electrode spacing here, indirectly electrode spacing refers to depth of penetration of the current. For different depths, how the apparent resistivity varied. So, if you are using Wenner method, you plot this with A. If you are using AB by, if you are using Schlumberger method, we plot this for AB by 2. If you use dipole method, we use N. What is N? N is the distance between two pairs. This is AB, this is MN, right. N is the distance between the center of this to this. This is referred as N. We didn't focus very much on dipole method, right, since most of our objectives can be answered with Wenner and Schlumberger method, right. So, we can try to understand about the subsurface by looking at the resistivity curve, right. That means, here is one plot, first plot A. The resistivity is continuously increasing. That means, the lower layer resistivity is greater than the upper layer resistivity. Isn't it? Rho 1 refers to resistivity of the topmost layer. Rho 2 is the second layer, rho 3 is the second layer and third layer and so on. Okay. So, by plotting the resistivity curve, what is resistivity curve? Resistivity curve is a relation between electrode spacing versus apparent resistivity. We are able to get an idea of the nature of the subsurface formation, right. In the second case, B, resistivity is continuously decreasing with the increase in the electrode spacing. What does it indicate? Resistivity of upper layer is greater than the resistivity of the lower layer, whereas here resistivity of the second layer is greater than the first layer. That is why the resistivity curve is increasing, resistivity values are increasing. Here resistivity values are decreasing. Then let us take up this case. Here what happens? Resistivity initially increases, reaches a maximum and then it goes down. The moment you see such a thing, mostly the deflection points, that is the change in the curvature, indicate the lithological contact. Okay. So, here we have three layers. This is layer 1, layer 2, this is layer 3, because this is electrode spacing. This is up to this is layer 1, layer 2, this is layer 3, 1, 2, 3. So, here what is the relation? So, apparent resistivity of layer 2 is very high. This is layer 2 is very high, higher than layer 3, layer 3 is higher than layer 1. This is the sequence of variation. We may get the next type like this. Resistivity is high, then it decreases, again it increases, right? So, here resistivity of layer 3 is the highest because it is the highest layer 3, right? Next is layer 1, next is layer 2. This is layer 2, okay. So, this is the difference. So, depending upon the contrast or depending upon the difference in the resistivity values, we are able to get different types of curves. And we are able to get these curves because we have progressively increased the spacing between the electrodes, right? Where when the electrode spacing is have to be very less than the thickness of the first layer, we have seen already. Only then we will be able to bring out the first layer. Suppose if you start, imagine the electrodes, the distance between depth to the first layer or thickness of the first layer is just 1 meter. If you start your survey by Venner method with a spacing of 3 meters, we are going to miss the first layer, isn't it? That is why we say spacing is very much dependent on the thickness of the first layer. Okay. Spacing can be much more if the thickness of the layer is very high. Imagine the first layer just below the surface, you have a very thick sandy layer of, let us say, 100 meters. Then you can have spacing between first value itself can be 75 meters. Okay. So, we need to decide about electrode spacing based on the thickness of the layers, right? To get apparent resistivity equivalent to true resistivity for intermediate layers, layer must be much thicker, right? This is also evident. For example, this is the ground surface, first layer is very thin, intermediate layer is very thick. Then the apparent resistivity value which we are getting for longer distances of electrode separation will be almost equivalent to the true resistivity of the second layer. Our rho A value will be equivalent to the true resistivity of layer 2. Okay. So, thus in vertical electrical sounding, we are obtaining the data of resistivity with respect to depth. How do we say depth? Indirectly, electrode spacing refers to depth. So, that is what we have achieved. So, interpretation is based on drawing a relationship between electrode spacing as well as resistivity, corresponding apparent resistivity. So, in this lecture, we have initially started with electrical profiling application, right? One application to bring out the buried channel, how electrical profiling was used. Then we have focused our attention to vertical electrical sounding, how vertical electrical sounding is carried out in a location. How this is carried out by progressively moving the distances between the electrodes. This can be also done by any method. By carrying out vertical electrical sounding by Schlumberger is little bit easier. Interpretation is made by drawing a plot of electrode spacing versus apparent resistivity. In the next lecture, we will continue to explore how the interpretation of the resistivity curve is made by different methods. Thank you very much.